Hello, Tanya Laird here, and welcome to part 2 of Lecture 10 of ENGR 231 Engineering Statics. In this portion of the lecture, I'm going to go over some of the theory and introduce the topic of analyzing trusses via the method of sections. So this is our second major tool of truss analysis. Our previous one was to consider trusses by looking at their individual joints and applying joint equilibrium. That is referred to as the method of joints. And you can see that in the Lecture 9 videos. So let us consider trusses, the method of sections. So let us say we have a truss of some form, and look at what kind of forces are going to be in it. So let's consider just a basic truss. All of the members, of course, being straight, having all the loads applied only at the joints, and all of the joints being pin joints. So just gonna draw out a little truss here. Make it a truss, a happy truss. Whatever. Maybe I'll just do something like this. A little faster there. This is turning out ugly. And there we go. Okay, so your basic truss. Now, let us consider what kind of forces keep this thing in equilibrium. So if we look at it from the global point of view, in terms of all the forces applied to the outside of the truss, this is going to be kept in place by rigid body equilibrium with the reaction forces, or via the reaction forces. So if there will be a variety of loads applied to the truss, including its own weight and any kind of forces from wind or rain or whatever the truss is carrying, etc., etc. And in terms of global stability, in other words, what's going to keep this truss in the position in space where it is the external reactions. But what about the internal forces? What about the internal forces? Well, in other words, what if I were to cut out a section of a truss and look at a free body diagram of just one piece of it? So imagine for a moment I were to cut this truss, and I were to isolate just one side of it. What kind of forces would be needed to keep that thing in place? So imagine I have a truss, and again, the central principle of the method of sections is that if an object is in equilibrium, in static equilibrium, I should say, any piece of it must also be in static equilibrium. Any piece of it must also be in static equilibrium. So consider this for a moment here. I'm just going to do a rough drawing of this truss. So I'm cutting across those, basically these three members. And what kind of forces are present there? I'm going to look at what kind of forces are present there. So we have our cut section of truss, and then our members that we cut across. Here, here, and here. Now we the loads that are on here, or the forces on here. First we have the forces that are external to the truss, the load and the reactions. But every time I cut across a member, I basically reveal an internal force. So there are other forces on this body, this one section of the truss that I cut out, and those forces are whatever member forces were originally on the truss, or inside those members. I shouldn't say on, I should say in this context. So you'd have whatever force was originally in the top chord member, whatever force was originally in this web member, and whatever force was originally in this bottom chord member. Here. And so another way of thinking about this is that if I'm going to keep this thing balanced, I need to apply certain forces in order to keep this thing in balance. In other words, like here, if these forces weren't present, let's say these forces aren't present, this thing, these three forces are no longer in equilibrium. This object is no longer in equilibrium. In order to keep in equilibrium, there must be some forces going through these members, and that's how the thing normally stays in equilibrium. And so if I were to cut it, well, in that case, if I were to cut this, then I would need to somehow replace these with forces, just pure forces. So the way I kind of like to describe the method of sections is something I may have mentioned in a previous video. Is that imagine I had a magic wand that I could go and, you know, I have this little magical wand and I can go up to things and just tap them and cast a little magic spell, and just out of nowhere a force vector appears. Just ex nihilo, out of nowhere a force vector appears. You know, I can just, if I tap it on a wall, that wall suddenly experiences a force of whatever pounds I specify or something like that. And so what I'm trying to show here is, if I could do that, if I could generate forces from nothing, what kind of forces would I need to apply to the truss in order to keep this section of the truss in equilibrium? And now, while we don't actually have a magic wand that can generate forces from nothing, and while there's really no need to, although that would be pretty useful, especially for rockets and such, but let's not worry about such things. But what's important here is that the forces that I would need to apply to keep this truss in equilibrium with my little magic wand are the exact same forces that would normally appear in those members. So this basic principle is what's going to be applied in the method of sections. And really, the method of sections is a rigid body equilibrium method. So the method of joints is a point particle equilibrium, or is an application of point particle equilibrium. In method of joints, if you remember from previously, we divide the truss up into its constituent joints. We reveal all, or draw all the forces that are present on each joint, and we apply a balance of forces to each joint to see what kind of forces are actually present, and then solve for unknowns, that sort of thing. But you're looking at each joint as a single point particle with a variety of forces applied to it. Now, with the method of sections, though, we are instead looking at a rigid body equilibrium. A rigid body equilibrium. So we're going to have a section of a truss, and we're going to look at what kind of forces are needed to keep this in place, and we're looking at what kind of forces are needed to keep it in place as a single rigid body. Okay, and the key thing about that it being a rigid body is that we're going to be looking at both sum of forces and sum of moments on this piece of the truss that we're analyzing. So here we're only looking at, with the point particle equilibrium, you're only looking at the sum of forces x, the sum of forces y, but then for the method of sections, we're going to be looking at sum of forces x, sum of forces y, and a balance of moments. But of course, this is for a 2D system. For 3D, it would be a bit more complex, but the same sort of point particle versus rigid body analysis would be present. Oh, that would be a fun one, using the method of sections on a space truss. That'd be a fun video to put together. Anyway, so let me actually just explicitly write out the steps of the method of sections. First, I generally recommend getting the external reactions on the truss if you can, because oftentimes you can get this, especially if the truss is simply supported or supported by only 3 reaction forces. You can often solve, well, if you have 3 or fewer, you can solve for those reaction forces using simple rigid body equilibrium applied to the entire truss. So, 1, if possible. Now, this cannot always be done, especially if you have like a pin-pin truss or a truss with multiple pins on it, that sort of thing. But that's why I will say, if possible, solve for the external reactions on the truss by treating the entire truss or analyzing the entire truss as a single rigid body. as a single rigid body. Two, figure out what member forces you're interested in. Which member forces you like or want to know. The nice thing about the method of sections, as we'll see, is that you don't need to move from one end of a truss to the other. You don't need to work joint by joint by joint. You can just jump directly to a final answer, or jump directly to an internal member force, and we'll see what that means. Determine which member forces you want. Three, carefully design your cut section. Carefully choose a section and cut. In other words, if you have your truss like this, maybe I'll draw it a little bit bigger. So let's see, what are some things that our cut should have? Let's look at some cut guidelines. So let's say I'm interested in these three members here. Let's say I'm interested in this member, and this member. Well, let's see. So the guidelines for the cuts are as follows. Maybe I can call this. Maybe I can use Roman numerals here. The cut, or should the cut or the section boundary should include all of the forces that you're interested in, if possible. Now, sometimes this is not possible. Every force you're interested in. Now, if I ask you for every single member force in a truss, if I ask you to find all the forces in all the members, then you're not going to be able to do that. You're not going to be able to do that with a single cut. I told you to do that using the method of sections, you would have to analyze that step by step and work through many different sections. But honestly, usually if I need to find all of the forces in every member, or the forces in every member, or the force in every member, I should probably say, I would just use the method of joints for that. The method of sections works really well if you are looking for just for a few member forces, but if you need to know every single member force, in that case you're usually better using the method of joints, but not always. 2, the member cut, or the section boundary, the cut / section boundary, can cross no more than 3 members. So I can do something like this, and that would be fine. Now, the reason I don't want to do more than 3 is that every single time I cut a member, I reveal an internal force. So think about that. Imagine if I cut this thing like this. How many members, and I tried to analyze this in rigid body equilibrium, like this piece here, or this piece. Well, actually, I guess I circled this one, so this piece here. When I cut across this member, I'm going to reveal an internal member force. When I cut across this member, I'm going to reveal an internal member force. When I cut across this member, I'm going to reveal an internal member force, and so on and so on. So when I have cut, this is a very poor choice of boundary, because when I cut it like this, I have now revealed 5 internal member forces. And since we're going to analyze this as a single rigid body, I would now have 5 unknowns on an object that I only have 3 equations of equilibrium for. So I would not be able to solve for all of them. I would have basically a statically indeterminate body because I chose my cut poorly. Much better is just a simple vertical cut like this. A simple vertical cut like that, because now I have 1, 2, 3 member forces revealed, and because of that, I'll have only 3 unknowns. I can solve for that. If you have 3 or fewer cuts or member cuts, you will have only 3 unknowns, and because of that, you'll be able to solve the system completely just using basic statics. And when I say basic statics, of course, I mean balance of forces and balance of moments. Now, let's see, what else? Oh, and the final key rule for our cuts. The cuts must only cross members, not joints. The cuts must cross members, not joints. So I sometimes have students, for lack of a better word, try to cheat. Well, not really, not like academic cheating, but like cheating in their analysis in a way. Because I tell them that, you can't have more than three, you can't cut across more than three members. They'll say, oh, aha, I have a solution. I'll just cut across the joints. There, now I haven't cut across any members. If I, kind of do this weird snaking thing and I try to cut through the joints and that sort of thing. While that is clever, and I'll give you bonus points for, I'll give you some accolades for being a little creative, unfortunately that doesn't work with the laws of statics. We can't really cut across joints in this sense, because when we are modeling joints anyway, we're considering, for example, when we look at the method of joints, we don't consider the dimensions of the joint. We treat them as point particles. So trying to cut across a joint is trying to cut across a point particle, really. And so a point particle, again, if you remember, is one with 0 dimension. And so yeah, you can cut across something that has actual dimensions like that. But if you're trying to cut across a point, something that by definition has no dimensions, well, you're basically trying to divide by 0 at that point, and it just doesn't really work out. Now, if you were doing this with more advanced techniques, like using mechanics of materials or something, and you wanted to use, say, a finite element analysis on a real joint, like I actually had a computer program that you had a gusset plate or something, and you were actually modeling the forces, in each cubic millimeter or something like that. Yes, in that case, you could think of it as cutting across joints. But if you're using a finite element model program anyway, you're not going to be really using method of sections anyway. These are hand techniques, not computer techniques. So anyway, so cuts must only cross members, not joints. Okay, and I think those are good rules for our cuts, and that should cover pretty much everything. 4, once you've done this, the cut, isolate the section, and reveal internal forces. And 5, isolate section, reveal internal forces. And finally 5, apply static equilibrium to the truss, to chosen section, and solve for desired forces. Solve for desired forces. So at a basic level, it's going to work like this. We'll have our truss. I'll just draw a quick one here. Quick-ish. Famous last words. Like so. And let's say for whatever reason I'm interested in this member here. Well, I'm going to choose a section that will include that force, that member force, and no more than 2 others. So I might just isolate, well actually to be consistent with my steps, I would first apply static equilibrium and solve for maybe that force and that force. Then I would isolate this section, and I think this would make a good section to choose, a good cut to use. And then I'll redraw it and say, okay, to basically draw a free body diagram of just this section. So I have this section here, this part of the truss, and then I'll replace all of the cut members with just their forces. Now, sometimes I do actually like to draw little stump members here, showing where they were cut, but really often I just draw the forces alone and ignore the cut members. Don't ignore drawing them. I just draw them as pure forces, but either is fine. So we have our reaction force here, and you'll have the forces that we're solving for here. Well, actually ultimately we were only interested in this one, and then I would apply static equilibrium to solve for whatever forces I wanted. Now, because I was interested in this force, a great way to do this would actually be to take moments about this point. Then I wouldn't have to solve for these unknown forces. I could just jump directly to the one I was interested in. And that really is the basic idea of the method of sections. In part 3, I will go through and work through a couple examples of this, but in this portion of the lecture, I just wanted to work through the theory. And really, I really want to emphasize that this comes from basic static equilibrium principles. And at a fundamental level, it is this basic principle of statics and Newtonian mechanics, is that, again, if an object is in equilibrium, every piece of that object must be in equilibrium. It's just like if I often just, if I'm teaching statics in front of a classroom, what I'll do is I'll stand in front of the classroom and I'll mention standing here, and I'll hold my arm out and I'll say, okay, imagine I were to cut out my arm. What would it take to keep this arm floating in space? Now, it's a kind of a grisly example, but it does get people's attention. And so, what would take to keep my arm floating in space here is some sort of upward force and bending moment to keep my arm in balance. If I could just remove it from remove my forearm from the rest of my arm or something like that. And so the same goes for my entire body. No matter where I cut sections out, there would always be some force revealed to keep that, whatever that is, in place, to keep that object in place. Or if I'm looking for a less grisly example, a common one I use is desks and tables. Tables are great examples in classrooms. So there'll be a table and there'll be multiple desks and tables, and I'll say, what if I were to come along with a great big saw and cut the desk in half? Well, there would be internal forces revealed, and there would be forces required to keep this thing in balance. And those forces that are required to keep that thing in balance happen to be exactly what forces are needed, or not needed, exactly what forces are present in the real body. And we'll use this later on when we get to shear and moment diagrams and internal forces in members. But this is the same basic principle as in the method of sections. All right, I think that'll do it for this portion of the lecture. This is just a basic video going through the theory and steps in the method of sections for analyzing trusses. And then in part 3, we will go through and actually look at some long-form examples. All right, that'll do it for now. Thank you for watching. Please let me know if you have any questions. I'll see you soon for part 3. And as always, thank you.